If you want to have a copy of this worksheet to work on as we go through it together, if you go into our Schoology page under materials, it'll be in chapter 4. And a good ways down here, we've done the 4.1 and 4.2 alternate examples, but you'll see this worksheet here that says observational versus experimental. That's the worksheet that we're looking at today. Okay. So first question we want to look at here, number 1, it says Jamie is a hardcore computer programmer. She and all her friends prefer Jolt Cola, caffeine equivalent to 2 cups of coffee, to either Coke or Pepsi, which have the caffeine equivalent to less than 1 cup of coffee. Explain why Jamie's preference is not good evidence that most young people prefer Jolt to Coke or Pepsi. So hopefully we said that, Jamie and all her friends, right, are not a representative sample of most young people, right? Since she's a computer programmer, her and her friends might have that interest in common and therefore have other things in common. So we wouldn't want to think of, if our population of interest is most young people or all young people, and then we have these programmers, all right? That's not going to be representative of the whole population. What we would want to do is take a more random sample, a simple random sample if possible, to get a better representation of the population. Okay, so the next one says, one study of cell phones and the risk of brain cancer looked at a group of 469 people who have brain cancer. Okay, so this group of people already have brain cancer. The investigators matched each cancer patient with a person of the same age, sex, and race who did not have brain cancer. Okay? So they took these 469 people, they looked at their age, sex, race, and then they found somebody who had all those things in common, but just did not have brain cancer. Then they asked each one about the use of cell phones. Our data suggests that the use of handheld cellular phones is not associated with risk of brain cancer. So I suppose what they found was that the amount of, they looked at these 469 people, so we get a person in this group, and we look at how often they use a cell phone, or whether they use it. They have some kind of metric on how to measure it. And then they compared that to the person who's like them, that doesn't have cancer, and determined how much cell phone use they had, and they compared them. And then after doing that, they said that they don't see any association of risk with brain cancer. So first and foremost, is this an observational study or is it an experiment? Let's answer that. Okay, so hopefully we said that this is an observational study, right? There is no treatment imposed in this situation, right? The people that have cancer already have cancer, right? They're also not imposing how often they're going to use a cell phone. In fact, it would kind of be pretty unethical to have people use cell phones more often and see if they're going to get cancer or more likely to get it. So as part of the problem with experiments a lot of time is ethical situations, but it is the more powerful tool in terms of trying to establish causation. But for sure, that's an observational study. Remember, the litmus test for observational study versus experiment is whether there's a treatment imposed. So, based on this study, would you conclude that cell phones do not increase the risk of brain cancer? Well, let's go ahead and answer that in the Ed puzzle. So it's going to be hard to make any conclusion from this because it's an observational study, right? So because this is an observational study, we can't really make a conclusion one way or the other. They don't have any evidence to suggest that there's a connection, but it's not really proof in one direction or the other because it was just an observational study. They're just looking at something arbitrary. And so they're saying risk of brain cancer, but we're always looking to talk about whether one thing causes the other. So with an observational study, it's very hard to make those kinds of conclusions. Okay, so let's look at number 3. Okay, so here we have an educational software company. They want to compare the effectiveness of its computer animation for teaching biology with that of a textbook presentation. So the company gives a biology pretest to each of a group of high school juniors and then divides them into 2 groups. One group uses the animation and the other studies the test. The company retests all students and compares the increase in biology test scores in the 2 groups. Is this an observational study or an experiment? Let's answer that first. So hopefully we said this is an experiment. And now let's talk about what's the treatment here, or treatments. Let's answer that. So there's two treatments right here. There's the one group that gets a treatment of using animation to study, and the other group studies the test. Okay, which would just be like the textbook presentation, right? They're comparing those two. So those would be your two treatments. And then they have their metrics to measure. Everybody took the same pretest, and then we look at an increase in scores on everybody took the same second test, and they compare the increase, right? If we get a bigger increase here in the folks that use the animation group, and they were randomly assigned, then we can reasonably attribute that change to the treatment of the animation. So if the group using the computer animation has a much higher, right? And when we talk about this statistical significance, this is important to stop and talk about for a second. So they don't use the term here statistically significant, but oftentimes we will, and we want to have an understanding of what that means. And we have not studied probability yet. That's what's coming next in Chapter 5. We'll start the building blocks of probability, but much higher, right? So what do we mean by much higher? We mean, and we can't really definitively say that until we start to study probability, which is coming next, but it means that it was so much higher that it's not likely that it would have happened by chance. It means that it's a pretty significant result. So to answer the part B, if the group using the computer animation has a much higher, a statistically significant higher increase than the group, what conclusions, if any, can we draw? Well, since it was a well-designed controlled experiment, right? They controlled for everybody took the same pretest, okay? They divide them into two groups. This is sort of the part that I'd be mostly interested in. How did they divide them, okay? If this was random, then we have good evidence that the animation is what caused the higher increase in the scores. If we said, who would like to use the animation and who would like to use the textbook presentation, we let the students choose that. Now we just induced a lurking variable, right? That could be a reason why a student would want to use the animation program as opposed to just study the test. That could be a result of the difference. So we've always in our experimental designs, we always want to make sure that we are randomizing the treatments. That's how randomization always comes into play. It's not so much that you're randomly selecting the students to participate. Once you have your students, you have to randomly assign the treatments so that we know there's no other factor or reason that would come into play as to why they would take that treatment. Okay, so let's go ahead and look at number 4 together. What's the best way to answer each of these questions below? We have 3 choices: survey, experiment, or an observational study. Okay, and a lot of times a survey is part of an observational study, but they can be a little bit different. Explain your choices for each, write a few sentences. We'll do this in a multiple choice fashion though. Let's take a look at the first one. Are people generally satisfied with how things are going in the country right now? Would we want to use a survey, experiment, or observational study? So hopefully you said there we would not really need to design an experiment to make that happen. We would send out a survey and maybe ask some questions about different things that might be related to a person's happiness. Could be their cost of living or employment situations, education, that kind of stuff. We could put out a survey and just ask people's opinions on how things are going right now. That would definitely be a survey. Okay. The next one. Do college students learn basic accounting better in a classroom or using an online course? Survey, experiment, or an observational study? So here, hopefully you said that we would need to do an experiment here, right? If all we did was an observational study, if we went, suppose we went to a group of students taking economics in the classroom and then another group of students taking an online course, well, we can't factor in what would drive a student to take an online course if they wanted to, right? So what we'd want to do is randomly assign some students to take economics or accounting rather in the classroom and some students to take it online, right? If we randomly assign that, and I've had a lot of experience teaching online classes, not just in this pandemic situation, but at a couple of different colleges. So, and I can say from experience that online classes are not for everybody. There's a nice convenience factor to it, but they oftentimes the majority of people really struggle with that and are not interested in it. It was really hard at Camden County in the fall where I had 3 classes that originally started meeting online and were meeting on campus. and were forced to go online. They didn't sign up for that, and students were in quite a panic. And I suppose many of you could relate to that as well. So it's very, very different. So to answer the question of whether people learn better in the classroom, we would not want to leave that up to somebody, the decision of somebody else to pick one of those. So we want to set up an experiment where we have, 20 students. We're going to randomly assign one group to a classroom situation and one group to the online course. And I also might suggest that you might want to control for something like the teacher or the professor. Have the same teacher teach both of these, right? And in fact, you could even make a block design, right? Suppose we have 4 teachers available for the experiment. So each teacher has a class of 10 in the classroom and then another class of 10 online. And then we look at how each teacher's classroom versus online course went. And then we could control for who the teacher is. That would be a pretty nice block design for that situation. And then the last one is this: survey, experiment, or observational study. How long do your teachers wait on average after they ask the class a question? So for sure, this could easily be done with an observational study. Right? Just hang out in class with a stopwatch. Let the teacher ask a question, hit the stopwatch, and see how long they wait, and take the average. Okay, so for this one, I might need more space than what I have here, but I want to at least try to set up the blocks so you can see how this is going to hash out. We have 20 overweight females, and they've agreed to participate in a study of the effectiveness of 4 weight loss treatments. So there we go. We know we have 4 treatments, A, B, C, and D. The researcher first calculates how overweight each subject is by comparing the subject's actual weight with their ideal weight. The subjects and their excess weights in pounds are the following. So the response variable is going to be the weight loss after 8 weeks of treatment. We know that a person's excess weight will influence the response. So what we mean by that is this: if somebody is more overweight than somebody else, maybe they'll be more likely to lose more weight, or vice versa. I mean, all we know is that it is a major factor. So it's going to be the deciding factor in how we would create our blocks. Now, since we have 4 treatments, we need 4 people in every block, right? The whole purpose of a block design, okay, is to group people that are as similar as possible by a factor that is going to influence the outcome. So the very first thing I would want to do here is talk about what my blocks would be. All right, so I have 20 overweight females, and if there's going to be 4 in each block, then I'm going to need 5 blocks. Okay, so let's take a look at our available subjects and tell me who ought we place in block 1. So hopefully you went through here and saw that Williams is the least overweight, right, by 22 pounds. Then we find that we have Dang, 24 pounds overweight. And then I have Hernandez and Moses, both 25 pounds overweight. So that would be my first block. Now, what would I do here? I would put all their names on a piece of paper, shuffle them up. The first name that comes out gets treatment A. The next name that comes out is treatment B. The third one that comes out gets treatment C. And the fourth one that comes out is treatment D. I need some kind of random way of assigning the treatments within that block. Okay? And you could, as it says, design an experiment, you write a sentence explaining that, right? Within each block, put the 4 subjects' names in a bowl, okay? And then randomly choose, the first one that comes out gets treatment A, and so on. You can just describe that in a sentence or two, okay? So now tell me what my next block would be. Let's keep moving in the same progression here. Who would be in my next block? So hopefully we came through here, again, systematically. Santiago is the next most overweight at 27 pounds. And then I see Kendall and Mann are both at 28 pounds. And then it looks like I have Smith at 29 pounds. That would be a suitable block. Okay, so let's list out the rest of the blocks here. Okay, so these would be the rest of my blocks. And then I want to write a sentence or two explaining, like we said earlier, how we would randomize them, and then how we would look at the weight loss after 8 weeks, and we would look at in each block, which treatment was most effective in block 1. Maybe it's A. maybe we find in blocks 1 and 2, A is most effective, but then in block 3 and 4, we find that treatment D was most effective, right? And then, so we can look at the who's most effective in each block, but then we could also just take an overall average effectiveness. We could take the average, we could take all 5 weight losses for A, all 5 for B, so we can, and average the weight loss, that total weight loss from A, total weight loss from B. So we can look and see what are the differences within each block, and then we can also look at the overall differences. Okay, that would be the right way to design that experiment using our blocks, controlling for the variable of amount of pounds, the amount of pounds somebody's overweight. I lost my whiteboard, and so on. Okay, so number 6 is always confusing for people. We'll see something like this on the test for sure, where you have to design an experiment. And this one says an industrial machine requires an emergency shuttle switch that must be designed so that it can be easily operated with either hand. Design an experiment to find out whether workers will be able to deactivate the machine as quickly with their left hands as with their right hands. Be sure to explain the role of randomization in your design. Okay, so you see the research question here. Okay, what's the treatment that's going to be imposed here? Let's answer that first. So hopefully you said that the treatment is going to be hand used, right? So if we know that treatment is going to be the hand use, we're trying to compare, so we're going to have, every candidate come up, and we could think about possibly making this a block design or a matched pairs based on handedness, and we could experiment separately on left-handed people and right-handed people. But I don't know if that's going to be necessary to answer their question. They just want to know if, in general, regardless of whether somebody's left-handed or right-handed, that they can operate this switch as quickly with either hand. Okay, so I don't know that the block design or the match pairs based on whether somebody's left-handed or right-handed matters as dominant hand. But how do we use randomization here? Okay, think about the experiment. I need every subject. It is a match pairs design. Every subject's going to operate the switch with their left hand and their right hand. So you're going to ask each individual to come up and use their left hand first and then their right hand. All right, and that would inject the lurking variable of they always use their left hand first. They got some experience using the machine, and then maybe all of a sudden everybody's faster with their right hand. Okay, so randomization would come into which hand they use first. Okay, and then we just subtract the difference in time. So we randomize which hand is used first. We have our, maybe 20 subjects. And then what we do is we see, okay, it took 2 seconds, 2.1 seconds, or 3 seconds, 3.2 seconds. Some people are going to have better hand-eye coordination than others, but we're controlling for that by making it a matched pairs design. Everybody operates the switch with each hand, and we randomize the order in which they do so. What do we measure or compare? The differences. And then we can take the average of all 20 differences, if we had 20 subjects, and compare that average to 0. If that average is significantly different from 0 in one direction or the other, then it would indicate to us that they're able to operate the switch more quickly with one hand as opposed to the other. And then we would, look to see, we would know right away because we should subtract the same difference every time. We're either going to do every time either take left minus right, okay, or take right minus left. It doesn't matter. Do one of those two, but do the same thing every time. So if it's negative and significantly less than 0, then it depends on which way we subtracted them. We'd know which one they operated faster with. Okay, can special study courses actually help raise SAT scores? Probably. One organization says that 30 students they tutored achieved an average gain of 60 points when they retook the test. Explain why this does not necessarily prove that the special course caused the scores to go up. Okay. So hopefully we notice what's missing here is a comparison group. We would need another 30 students to take the SAT and then take it again in the same amount of time that these other folks were taking this special course, and maybe they study on their own. In general, people's scores usually go up the more times they take it. So just from the simple experience of taking the SAT, next time you take it, it's likely to go up. propose a design for an experiment that could test the effectiveness of the tutorial course. Okay, so in this situation, the treatment is going to be the tutorial course, right? That'll be our treatment. Let's take another 30 students, right? So we have 60 students. We randomly assign them to either take the course or study on their own. All right, retake SAT. Right? And what we want to do is measure average increase, okay? Because some students are going to get higher scores than others anyway. So we measure average increase. And we do that for both. And then we would compare them. Okay? So suppose on average, people that don't take the course, their points go up 30 points. Well, then these folks could probably only attribute 30 points to the of the achievement and increase to their course, not the whole 60. Suppose you suspect the tutorial course might be more powerful or more helpful for students whose initial scores were particularly low. How would this affect my design? We could make a block design, right, based on initial scores. So you could have, at least 2 blocks. You could say initial score low and then run the exact same experiment, okay? However many people that had low scores to begin with, but then you do the same experiment, all right? Except you wouldn't start with 60, you'd start with however many were low and then high scores. Or you could have low, average, high. But you're gonna have to decide ahead of time what those numbers are. So we take everybody's initial scores, group them together in groups as similar as possible, like we did up here, okay? And then we randomly assign them to the same 2 treatment groups. Take the SAT, or take the course, or just study on your own. And then we measure the differences again, except we would have several blocks, right? We'd have a low and a high. And then we do the same thing in these 2 blocks that I just did previously. Okay, so here we want to think about in this last example, hoping to learn how to control crop damage by a certain species of beetle, a researcher plans to test 2 different pesticides. Okay, so those are his 2 treatments in small plots of corn. Okay, a few days after application, he'll check the number of beetle larvae found on each plant. Okay, wants to know if either pesticide works and whether there's a significant difference in the effectiveness between the 2. So let's think about, in this experiment, what are some things he might want to control for, right? He'd probably want to make sure that they all get the same amount of sunlight, water, right? And then also, how about location? So maybe if he has these small plots, each plot could be a block. So I have 1 plot of corn, and then I randomly assign the treatments. I just want to close out by thinking about the 4 parts of our experimental design, right? He could control for the sunlight, water, location, randomly assign the treatments, compare plants in the same plots if that's an option. If they are, if it's reasonable to make a block design out of this, we could describe it. There's not a ton of information here suggesting that we ought to do a block design like we did up here. This is making it pretty obvious that a block design would be necessary. We could just go to different plots, but it makes sense to me. I could picture a plot of corn, randomly figure out a way, number each plant inside that plot, and then randomly assign half of them to get 1 treatment and 1 pesticide, and the other half get the other type of pesticide. So, because location of plots could, like with the sunlight and those things, be a huge factor. And then replication just means that, maybe we have 20 of each plant that gets, 20 pesticides on 1 plant, 20 of the other 2 pesticides on the other plant. That's where we see our replication in that situation.